In the last class, we studied about PAPR reduction techniques, which reduce PAPR along with the signal distortion. Today, we'll study the other class of PAPR reduction techniques, which preserves the information, which doesn't cause distortion for the original PAPR signal. We don't lose any information in the OFDM signal, and these are multiple signaling and probabilistic techniques. And these techniques works in two ways. One way is to generate multiple permutations of the OFDM signal and transmit the one with the minimum PAPR. And the other way is to modify the OFDM signal by introducing phase shifts, adding peak reduction carriers, or changing the constellation points. And we'll see certain methods which deal with these techniques, multiple signaling and probabilistic techniques. The key point you have to note here is these techniques, multiple signaling and probabilistic techniques, they don't induce distortion to the signal. They preserve the whole information in the signal. The first method we are going to learn is selective mapping. Selective mapping. Selective mapping, short form is SLM. SLM is a relatively simple approach to reduce PAPR, and the idea is to generate a set of sufficient different OFDM symbols XM, where M varies from 0 to M minus 1, each of length N, all representing the same information in the original signal X. Then transmit the one with the least PAPR. So you can see the diagram here, where there is the incoming binary data. Constellation mapping modulation is performed. Then there is a serial to parallel conversion. And before IDFT, what happens is these signals, the signal that you get here after serial to parallel conversion, which are basically serial to parallel converted modulated symbols. These symbols, they get multiplied by sequences P0, P1 up to Pm minus 1. So let me brief you about how these sequences look like. These are basically phase sequences. P0, P1 up to Pm minus 1. These are phase sequences. Which means their magnitude is unity. It doesn't add power to the signal. Its magnitude is unity, but it has a phase factor. It has an angle factor. So you can see here PM has the phase signals e raised to j phi m comma 1, e raised to j phi m comma 2, and it goes up to e raised to j phi m comma n. So these signals which comes after serial to parallel conversion. So here you have the original binary signal, some binary data. After mapping, you will have these converted into corresponding modulated symbols. So let that be x1, x2, etc. up to xn. And these are converted, serial to parallel converted, where each of this, let me just write it down here. So at this point you have the original signal, OFDM signal, not OFDM signal, the signal after modulation, which is x1, x2 up to xn. Okay, x1, x2 up to xn, and these symbols. Okay, so this symbol comes here, x, same symbol comes here, same symbol comes here, and you have P naught getting multiplied with each of these signals. So at this point, so let me draw it a little more neatly. So at this point, you have the signal x. I'm not going to repeat it again. The signal x. X is multiplied with the sequence P naught. So P naught is again an endpoint sequence. So this is basically, let me write a bit more neatly here. So you have x here, which is x1, x2, etc. up to xn. These are the modulated symbols. They are getting multiplied by sequence P naught here. X is getting multiplied by P naught, so you have x into P naught, which means you have P naught. P naught is equal to, according to this expression, substitute m equal to 0, you have P naught. P naught is equal to e raised to j phi naught comma m e raised to j phi naught comma 1. Next expression will be e raised to j phi naught comma 2, etc., etc. It goes up to e raised to j phi naught comma, and these two get multiplied. X gets multiplied by P naught, and you have here x into P naught. So I should actually mark it like this. Okay. So this is P naught. P naught is this quantity, and here you have x into P naught, x into P naught, which is basically a multiplication of these two, x1 into e raised to j phi naught comma 1. That is the first term. Second term will be x2 into e raised to j phi naught comma 2, etc., etc. It goes up to xn into e raised to j phi naught comma n. So you have the term here x into P naught, and similarly you will have x into P1 here, where P1 is going to be e raised to j phi 1 comma 1, e raised to j phi 1 comma 2, etc. goes up to e raised to j phi 1 comma n. So they will have a different phase sequence. P1 is also going to be a phase sequence, but it is different from P naught. So this x signal x is getting multiplied with P1 again, and you will have from here you will have x into P1, which is having a similar expression to this. Instead of e raised to j phi naught comma 1, here it will be e raised to j phi 1 comma 1. Just like this expression, where you substitute values from m equal to 0 to m minus 1, you will have different values for p naught, p1 up to pm minus 1. And here this goes up to p naught, p1, it goes up to pm minus 1, and here you will have x into pm minus 1, m minus 1, you will have this. And so before IDFT, you have x into p naught here, x into p1 here, x into pm minus 1 here. Basically the same signal x is getting multiplied with different phase sequences having a length of n, having a length same as the length of the set of modulated symbols. Having this modulated symbols is having n number of symbols. The same, so each of these symbols are getting multiplied by the phase sequence, each element in the phase sequence, and we have phase sequences from p0, p1 up to pm minus 1, and you have correspondingly x into p0, x into p1 up to x into pm minus 1, and then this and it is shown here. Okay, you have like this, where x naught m varies from 0 to m minus 1. So you have these symbols xp0, xp1 up to xpm minus 1, and IDFT, and endpoint IDFT is taken, and you will have here x in bracket subscript is m. So you have here x naught, you have here x1, you have here xm minus 1, and then the sequence with lowest PAPR is taken. Basically x0, x1 up to xm minus 1, all these represent the same information. Only difference is that it got multiplied with some phase sequence, and this phase sequence, according to which phase sequence is getting multiplied with x, you will have different values for PAPR for each of these signals. Remember, this PAPR is caused due to addition of signals with same phase at any particular time. So these phase sequences, what they do is they try to alter the phase of these subcarriers, and we are not sure how it will alter, how each phase sequence will alter each signal x. This x is different at every time. X symbols are getting blocked and getting ready for transmission using OFDM, and x varies from time to time, and we don't know which phase sequence is going to have the lowest PAPR, which phase sequence when getting multiplied with x is going to have the lowest PAPR. So this device here, this block here, it is going to select the signal with the lowest PAPR, where we will have m, capital M phase sequences, and out of these phase sequences this block will select the sequence with the lowest PAPR value, and that is getting transmitted. That is x tilde. X tilde is a sequence with the lowest PAPR value. So that is represented here. X tilde is argument minimum of PAPR of x of m. where m ranges from 0 to m minus 1, and the signal with the minimum PAPR is transmitted. That is this parameter x tilde. X tilde is a signal out of the m symbols. The symbol with the lowest PAPR is x tilde. Okay, and these phase sequences PM, there are capital M phase sequences P0 P1 up to P0 P1 up to Pm minus 1. There are M different phase sequences, and the elements inside the phase sequences are these complex exponentials. So being a complex exponential, its magnitude is equal to 1, and it has got only the phase value, which changes the phase of the OFDM signal when it is getting multiplied with this sequence. And this complex exponential, it can have its angle phi m. Phi m can be varying from 0 to 2 pi, where 2 pi is not included. It varies from 0, this is a set, 0 to 2 pi, where 2 pi is not included. It ends just before 2 pi, because 2 pi is same as 0 angle. So these phase sequences can have elements whose angle varies from 0 to 2 pi, where 2 pi is not included. That is the meaning of this. Here you have a square bracket, and here you have the ordinary bracket for k equal to 1 to up to n. And so that is the whole idea of selective mapping. So selective mapping, basically what it does is it multiplies the modulated symbol with m phase sequences, and these phase sequences which has the same length as the incoming signal x, the modulated set of symbols x. They change the phase of this signal x. So each of the phase sequences, they are different. They have different elements in it, and these elements, they have a unit magnitude, and they have the angle phi m comma 1. They have the angle which ranges from 0 to 2 pi, and these phase sequences are different, so they induce different phase rotation for the original set of modulated symbols. And after DFT, IDFT, the sequences that you get x0, x1 up to xm minus 1, out of these sequences, the sequence with lowest PAPR is selected and it is transmitted out. So this is the idea of selective mapping. Okay, it is the idea of selective mapping, or in short SLM technique. Now how does the receiver know which phase sequence was multiplied with the original modulated set of symbols? Only then the receiver will be able to regenerate, or only then the receiver will be able to identify what was the original value of x which got multiplied, right? When you think in the receiver, you can do an inverse of this phase sequence, but how does the receiver know with which sequence the x got multiplied? From P0, P1 up to Pm minus 1, there are m different phase sequences, and which phase sequence got multiplied with x. So that information also has to be sent along with the transmitted symbol x tilde. So along with x tilde, there is another information that you need to transmit, and that is which phase sequence got multiplied with x. And you have m number of phase sequences, so you need log m to the base 2 bits to represent this information m. So you need at least log m to the base 2 bits to represent this information. So if you have four four phase sequences, so you can have log 4 to the base 2, which is 2. 2 bits are used to represent each of the phase sequence. So you can have 0, 0, 0, 1, 1, 0 and 1, 1. 2 bits used to represent each of the phase sequences, right? So this is actually an overhead information. So it is not the information. It is not part of the original information, but it is an information. It is a information which is required to decode the signal. It is called as a side information. Okay, it is a side information. So along with x tilde, you also need to transmit the side information to the receiver. Only then the receiver will be able to decode the original signal, right? That is one of the disadvantages of SLM technique. One of the disadvantage of SLM technique is the side information need to be transmitted. So side information is actually an overhead information. So it is an information information which is not part of the original information, but it is an essential information just to know which phase sequence got multiplied with it. So this side information, so you need some energy to transmit the side information also. You need some method to transmit the side information also. So you are going to definitely lose some data rate over there in order to transmit the side information. For every x tilde, you need to also transmit the side information. That is one of the disadvantages of the SLM technique. Another disadvantage is that these phase sequences Pm, where m varies from 0 to m minus 1, so capital M phase sequences, they need to be stored at both transmitter and the receiver. Okay, so you need some storage. Okay, store phase sequences. You need to store the phase sequences. So there are m phase sequences. Each of the phase sequence is having a length of n. So you need some memory to store these phase sequences. And also another very important drawback of SLM is that if the receiver decodes the side information wrongly, if there is an error in decoding the side information, then the phase sequence is going to be wrong. The phase sequence is going to be wrong. So erroneous detection of side information causes the whole OFDM symbol to be recovered incorrectly. So erroneous detection of side information, it makes the whole OFDM symbol to be detected wrongly. The whole OFDM symbol is going to be wrong. The whole OFDM symbol is going to be in error. So that is another disadvantage of SLM technique. So you need to have this side information transmitted with maximum signal to noise ratio. So what we usually do is we transmit side information with more power. So because if the side information gets wrong, then the phase sequence gets wrong. And if there is a wrong sequence, then the inverse of that sequence is going to be wrong, which makes the whole OFDM symbol go wrong. Therefore, this side information need to be transmitted at a higher SNR. Only then you can be sure that your phase sequence that you decoded is correct. Another disadvantage is that if the value of if the the size of the OFDM block n, if the value of n is large, if the value of n is large, then the number of how many memory you need to have. If the value of n is large, or if the value of m is large, then you need to have your storage is going to increase, right? Remember, m is having the same value. M is having, each of the phase sequences are having a length of n. So if you have m phase sequences, each of length n, so you need to have m into n units of storage space. And if the value of n is large or m is large, then the storage you need is going to increase, right? The storage you need is going to increase. So it may not be completely computationally feasible if the size of these blocks are large, because here you have a selection block. Selection block is basically an optimizer. Okay, it does an optimization. It checks the PAPR of each of these signals, and then it selects the one with the minimum PAPR. It is optimized to select the signal with the minimum PAPR. And this block is going to have a lot of load. It is going to have a lot of workload, or computationally it is going to get intense when the value of n is going to be large, or when the value of m is going to be large. This optimization which happens here in this block is going to be very difficult. Another disadvantage you can very easily see is that if the value of m is large, you need so many IDFT blocks. If you have m number of phase sequences, you need m number of IDFT blocks. You need so much of hardware. You need m number of IDFT blocks. So the extra hardware you need will be more. And if the value of n is large, right? If the value of n is large, then the number of computations are going to increase. You might have learned that if you are taking an endpoint FFT or an endpoint IFFT, your number of computations are n log n to the base 2. And if the value of n increases, then proportionally the number of computations are going to increase. So all these are different, even though we have an advantage of selection of the signal with the lowest PAPR, you also have all these associated disadvantages for selective mapping method. The next method we are going to learn is a partial transmit sequence, which is not so computationally extensive like SLM. Partial transmit sequences, short form is PTS. PTS is a not so complicated method, but PTS has again its associated complexities. We'll see how this is done. You can see the block diagram of partial transmit sequence. You have the binary incoming data. It is getting converted to modulated symbols, and serial to parallel conversion is done. And then you have a block for PTS, that is division into subblocks. It is getting divided into subblocks. And these blocks are, you have m number of subblocks. These are x1, x2 up to xm. And then an IDFT is performed. After IDFT, you have the time domain signals, and these time domain signals, they are given to an optimizer. Optimizer is basically a processor. It selects the value of sequences bm. here the sequence is BM. It is definitely a phase sequence, but it has some differences when you compare with SLM. We'll see what it is. So these optimizer selects the value of this BM, and it gets multiplied with x1, x2 up to xm, and finally all these are added, all these are combined, and all these are added, and it is getting transmitted as x. So where does the optimization happen here? Optimization happens in the selection of B1, B2 up to BM. The selection of B1, B2 up to BM, it is done by an optimizer, and these selection of sequences, they are based on the values of the subblocks x1, x2 up to xm, which are the time domain equivalent of the subblocks. So we'll see how these subblocks are formed. Yeah. So you have binary data here. It is getting mapped to modulated symbol. So let me just write that here. Yeah. You have these modulated symbols. X1, X2 up to, okay, let me just be more specific. X3, X4, X5, X6, X7, X8, X9. Okay, so I'm just taking a specific example. It could be any value. I've just taken a 9-point sequence here. So you have, after mapping, you have here this particular block. Just make it up to X8 because, yeah, because mostly the input to IDFT blocks, they are multiples of, they are powers of 2. If you want to do FFT or IFFT algorithm, the hardware architectures are so designed such that they are powers of 2. So let it be like this: x1, x2, x3 up to x1 up to x8. All these symbols, they are being mapped, and this block divides it into sub-blocks. Okay, so what does that do? So division into sub-blocks, and they divide into m number of sub-blocks. In the example which I'm doing, I'm dividing it into 4 sub-blocks. Okay, I'm dividing it into 4 sub-blocks. So these sub-blocks, they are orthogonal to each other. Okay, that is a speciality. When you divide this into sub-blocks, they are orthogonal to each other, and X is a combination of all these sub-blocks. Okay, let me just demonstrate that to you. So the first sub-blocks that I have here is x1. So this whole sequence is x. So the first subblock that I have here is x1. So I have used the same convention here, but don't get confused. So let me write it with a different color. Okay. Yeah, I have here x1, which is x1, x2, and the remaining all are zeros. Okay, I have x2, which is x3, x4, x3, which is 0, 0, 0, 0, and x4, which is again 0 0 0 0, and you have x7 and x8. So you can see if you multiply any of these sequences, you are going to get a value of 0. And if you add all these sequences, summation x m, where m equal to 1 to 4, you are going to get back the original sequence x. So that is shown here in this equation. You add all these sublogs and you're going to get back the original signal x. And after dividing these sublogs into this, then an IDFT is taken. IDFT is going to be again an endpoint IDFT, and the time domain equivalent of these sublogs x1, x2 up to xm, they are given to an optimizer to select the value of bm. They are given to the optimizer to select the value of bm, and bm is a phase factor. Bm is a phase value, right? But it is only a single value. It is not a sequence. It is a single value. bm is a single value. So you have m varying from 1 to m, and your phi m, the angle this complex exponential can take, it can vary from 0 to 2 pi, where 2 pi is not included. And you can have uh, bm, m, where m is varying from 1 to m. You can have any of the m sequences. And what should be the value of m? What should be the value of b1, b2 up to bm? That is decided by the optimizer based on the values of IDFTs x1, x2 up to xm. The optimizer decides the value of bm's, b1, b2 up to bm, and each of these symbols x1, x2, x1, x2 up to xm, they are getting multiplied with bm, which is decided by the optimizer, and you have an addition of all these signals. So here you will have x1 multiplied by b1, here you have x2 multiplied by b2, here you have xm multiplied by bm, and the addition of all this will give you the signal x, which is getting transmitted. X is getting transmitted. And will x have a low PAPR value? That is defined by the optimizer. Optimizer selects the value of bm. Bm is basically a phase value. So each of these signals x1, x2 up to xm, they are multiplied with phase values b1, b2 up to bm, and they are added to give the signal x, which is getting transmitted. So if you have assume that the set of allowed phase factors is defined as bm, where bm is equal to e raised to j 2 pi k divided by w, where k varies from 0 to w minus 1. So you can have phase sequences, allowed phase sequences. Suppose allowed phase sequences are there are w allowed phase sequences. Okay, these are allowed phase sequences, and so you have bm which can take any value e raised to j 2 pi k divided by w, where k can vary from 0 to w minus 1. So correspondingly this can be e raised to j 2 pi 0 by w, or it could go up to e raised to j 2 pi into w minus 1 by w, which is basically a variation from 0 to 2 pi. So you have w number of allowed phase factors. You have w number of allowed phase factors. Usually the first phase factor B1, it is set to 1, which means this symbol signal x1 will get multiplied by a phase factor 1, which means it doesn't have any change for the signal. So the output of this multiplication is going to be x1 itself. It doesn't impose any change for the signal. And then you can have b2 up to bm, b2 up to bm. You can have m minus 1 phase factors getting multiplied with these time domain signals. So you can, if you set b1 to 1, then m minus 1 phase factors are found to be existing. And how many combinations are possible? So you have when you have m minus 1 phase factors, so b2, so b1 is 1, it is fixed, b2, b3 up to bm, bm, okay, this bm, you can have m minus 1 allowed phase m minus 1 phase sequences getting multiplied here, and b1 could be any of the w allowed phases, b3 could be any of the w allowed phases, bm could be any of the w allowed phases. And how many combinations are possible? You can have here b2, b3 up to bm, you can have m minus 1 number of possible combinations, m minus 1 number of places here. So you have w multiplied m minus 1 times, so w m minus 1 possible combinations of phase. Okay, I hope the idea is clear for you. So there are w allowed phase sequences, there are I must say phase factors. Okay, there are w allowed phase factors, and the first phase factor here, b1 is set to 1. So you will have phase sequences from b2 to bm, and each of these phase sequences, there are m minus 1 phase factors. Each of these phase factors could be any of the w allowed phase factors, and so you have m minus 1 places here, m minus 1 phase factors. Each of the phase factor could be any of the w allowed phase factors. So you have w m minus 1 different combinations of phase factors. So the optimizer needs to search wm minus 1 combinations in order to find the correct combination, in order to find the combination of phase factors which gives the minimum value of PAPR. Right, that's the idea. So this optimizer, what it does is it performs a search over wm minus 1 phase factors. It simply substitutes each combination of phase factors and try to find the phase factor which has got the minimum. Try to find the set of phase factors. Try to find this set of phase factors which has which when multiplied with time domain signals x1, x2 up to xm, that gives the minimum PAPR when you add all these sequences. So there lies the complexity of this process. And as the value of m increases, it is going to be an exhaustive search. So that is one of the disadvantages of PTS method. That is, when the m is large, value of m is large, then if there are w allowed phase factors, then you need to search over wm minus 1. So that number is going to be a large number if the value of m is large. You need to have a search. The optimizer needs to have a search over wm minus 1 phase sequences in order to find the optimum phase sequence, the phase sequence that gives you minimum PAPR. And you can clearly see that if you increase the value of m, then obviously you will have a better optimization. But if you simply increase the value of m, then this possible combinations, the number of possible combinations is going to increase exponentially by this value. And so the complexity is going to increase. So the computational complexity is going to increase considerably. The computational complexity is going to increase exponentially. Okay, you have an exponent w raised to m minus 1. You have an exponential increase in complexity if the value of m increases. And also the second disadvantage you can very well see here is you need to have m number of IDFT blocks. So that is an extra hardware you need to have. When conventional OFDM has only one IDFT block, you need to have m number of IDFT blocks. So that is another disadvantage of PTS technique. You need to have m IDFT blocks. Okay, you need to have m IDFT blocks, right? Also, when you have m IDFT blocks, the receiver needs to know which is the phase combination, which is the combination of phase factors that was transmitted, that was used in the transmitter circuit. Okay, you have wm minus 1 number of combinations for phase factors. You used one of them. The optimizer found one of the phase factor to be optimal in nature, which has the lowest PAPR, and this information has to be transmitted along with the OFDM signal. So that is a side information. Again, you need to have a side information which should get transmitted. And in order to transmit wm minus 1 combinations, you need at least log wm minus 1 to the base 2 bits of so many bits of information. So along with the OFDM signal, which is having the lowest PAPR, you need to transmit this side information, log of w raised m minus 1 to the base 2. That also needs to get transmitted for the receiver to know which combination of phase sequence was used at the transmitter. Another factor is, this is not a disadvantage, it is a feature, is that the third, it cannot be called a disadvantage, it is a feature of this technique that affects the PAPR, is a type of partition. The type of partition, the partition which I have used here is adjacent. Okay, adjacent partition, which means all these are adjacent subcarrier, all these are adjacent subcarriers, or all these are adjacent symbols. They lie close to one another. So this is one type of a partition. You can also have an interleaved partition where this is going to be here it is going to be x1, and here it is x2, here it is x3, here it is x4, and it can go like that, an interleaved partition, or it may have okay, I'll just demonstrate to you the interleaved partition. So interleaved partition, it will look like x1 is going to be x1 0, x3 0, x5 0, it could go like that, and x2 will be 0, x2 0, x4. So basically an interleaving is happening here. Partition could be done like that. Even then the signals, the subblocks will be orthogonal to one another, or a pseudo random partitioning can be done. But pseudo random partitioning, the signals are orthogonal, but it doesn't follow any pattern. It is a pseudo random partitioning that is being used. It doesn't follow patterns like this, and pseudo random partitioning is found to be the best choice among the different types of partitioning. But if you have pseudo random partitioning, again, which type of for every sequence the type of partition is going to be different. Again, that information needs to be transmitted to the receiver, so the amount of side information again is going to increase if you are using pseudo random partitioning. So I hope the idea of PTS, partial transmit sequence, is clear for you. The next method that we are going to learn is interleaved OFDM. So interleaved OFDM is similar to SLM, selective mapping. And if you know selective mapping, this is going to be really easy to study. That is the incoming binary data, it is being mapped with some constellation, a modulation is happening there. And this sequence, just like selective mapping, the same sequence goes to interleavers, and interleavers, they interleave the incoming signal by using some permutation, and these permutations are going to be different for each of the interleaver. Basically they are trying to have different combinations of signals. The first so here the signal goes as such, so x goes as such, x is x1 x2 up to x3 x4, maybe it's a 4-point sequence. X goes as such here, IDFT is taken, x yeah, this is x1, x2 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 can be so x1 is same as x itself, x2 is a permutation of x, so it could be like this, x2 x3 x1 x4. After interleaving, it could become like this. Okay, here again there is another interleaver which makes another combination of this signal x, and different interleavers they give different combinations of your input signal x, and these go to IDFTs, and here you have a block which is the block which is same as that you saw in SLM method. It selects the signal with the minimum PAPR value. Again, the disadvantages that you saw in selective mapping also happens here. Almost even I can say this technique is almost similar. Here you have m interleavers, so a side information of log m to the base 2 bits, so many bits need to get transmitted. Side information is an overhead information. It will reduce the data rate of original OFDM transmission, and you need a m number of IDFT blocks, which calls for the requirement of additional hardware. Again, these interleaving patterns, they have to be stored stored somewhere, both in the transmitter and the receiver. This information, interleaving information, this permutation format, it has to be stored in both transmitter and the receiver. So you need some storage. And the block here, which selects the one with the lowest PAPR, the computational complexity is going to increase if the value of m increases or if the value of n increases. And the CCDF, complementary cumulative distribution function, will be is defined like this for this interleaved OFDM. It is defined like this. Here 1 minus, I'll just highlight it, 1 minus e raised to minus del whole raised to alpha n, where del is a threshold value, okay, some threshold value. Alpha is an oversampling factor. N is the size of the OFDM symbol. N is the size of OFDM symbol. So this term 1 minus e raised to minus del whole raised to alpha n, that is the CCDF of PAPR of an OFDM signal, of a typical OFDM signal without any PAPR reduction technique. CCDF of PAPR of xn of t is this value, 1 minus e raised to minus del whole raised to alpha n. Each of these interleavers, they are independent of each other. And so you have this term multiplied m times or whole raised to m. So that becomes a CCDF of interleaved OFD. Okay. So that's about the few PAPR techniques which come under this multiple signaling and probabilistic techniques. So these techniques, basically what they does is they try to generate multiple permutations of OFDM signals. So SLM, PTS, interleaved OFDM. They try to create multiple permutations, and they transmit the signal with the lowest PAPR value. Let me go back to this PAPR overview of PAPR reduction techniques. We have learned about the different signal distortion techniques in the last class, and now in this multiple signaling and probabilistic methods, we learned about selective mapping, PTS, and interleaved OFDM. And there are also other methods like tone injection, tone reservation, active constellation shaping, and constrained constellation shaping, which tries to give some modification for the original constellation and tries to reduce PAPR in that manner. So we'll study such methods: tone injection, TI, tone reservation, TR, active constellation shaping, ACS, and CCS, constrained constellation shaping, in the next class. Thank you very much.